Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about non-ideal systems. So previously we were able to develop a series of non-ideal equations based on the internal energy. Today we're going to go ahead and use these same ideas, but move on instead to looking at enthalpy. Because again, just like we were able to build up from the idea that the internal energy is both volume and temperature dependent, we can do the same thing with enthalpy by looking at pressure and temperature. Now, doing this, we can go ahead and just take the series of partial derivatives to show that the change in enthalpy can be based on changes in pressure and temperature. Now, this leads us to having two prefactors. The isothermal change in enthalpy with pressure, and the isobaric change in enthalpy with temperature. Well, it turns out this second term should look fairly familiar because it's the isochoric heat capacity. Now, what this leaves behind is our need to look at this second term, the isothermal change in enthalpy with pressure. Now, this is often in practice broken into two bits because we can more or less use the chain rule to split this integral into this derivative into half. We can go ahead and first look at how the enthalpy changes with temperature under isobaric conditions, so keeping that pressure constant. Then we can go ahead and move that temperature back to where it should be under isenthalpic conditions. So first letting the pressure change, or the enthalpy change, and then letting the pressure change. Now, when we do this, we end up with two terms. Again, this first term should look fairly familiar. It's going to be simply the isobaric heat capacity. But we get this new term, this mu, and this mu stands for the Joule-Thomson coefficient, or again, the isenthalpic change in temperature with pressure. So again, if I go ahead and increase the pressure of the system, how much would I expect the temperature to change? Now, this can go ahead and be related to that full integral by the negative of 1 over Cp and then that uh, isothermal change in enthalpy. Now, it is worth noting that we're often going to be talking about the Joule-Thomson coefficient, but you will occasionally encounter something called the isothermal Joule-Thomson coefficient, which you can tell the difference because it's just going to be that mu with a T subscript, meaning the temperature is constant. And that's going to reference that actual derivative we're really interested in of this change in enthalpy with pressure. Now, again, because of the relationship in between the split derivative, this will be the same thing as negative Cp times the Joule-Thomson. So again, if you need to convert between the isothermal Joule-Thomson and the Joule-Thomson, you're going to need the isothermal heat capacity or the isobaric heat capacity, which is fairly easy to obtain. So what we can do is we can now redescribe our general equation for the change in enthalpy in terms of pressure and temperature in one of two ways. We can either base it on this heat capacity in Joule-Thomson, or we can just use the isothermal Joule-Thomson. These two formalisms are equivalent. We've just substituted in the isothermal Joule-Thomson. But regardless, if I'm going to try and derive this full equation, well, we know plenty of good ways to determine the heat capacity. The real problem child here is going to be figuring out that Joule-Thomson coefficient, which has a mild problem of its measuring the isenthalpic change in temperature. So we need to figure out how we can look at a system that has constant enthalpy but still has changing temperature and pressure. Well, it turns out one of the best ways to do this is you can let a gas expand from a high pressure area to a low pressure area. So that gets us the changing pressure, and then we can simply measure how the temperature changes. But how can we make sure that the enthalpy doesn't change? So one of the classic oversimplifications of this case is going to be looking at the compression of a gas through a throttle. So we're going to take a gas with initial pressure volume, and then we're going to compress it to pretty much a very small volume, and then we're going to let it expand. In practice, we can never get that volume to zero. We might be able to get it near zero, especially if we have a solid surface, but it'll be hard to do it. So this is kind of an over-exaggeration, but because of the nature of state functions, as long as I have the right initial state and final state, it doesn't matter how I do it. So I can go through a non-realistic intermediate. And the goal of this is going to be showing that this compression followed by expansion is isenthalpic. So we go from a high pressure to a low pressure. The big thing here is we're going to be doing this in an adiabatic chamber, which as a reminder means that we're not allowing heat to come in or exit. So this will be at a fully insulated piston. Now we can figure out the work for each of these two steps, first for the compression and then the expansion. So again, in each of these cases, we're going to assume that both the compression and the expansion occur isobarically. So we can get the work for the system simply as negative P delta V. So we know the initial pressure, and the change in volume is just going to be going from the initial volume to a volume of zero. Now, this gives us a work of the pressure times the volume. Then for the expansion, this is again still going to be negative P delta V. And if we allow this to occur isobarically, it means it will expand against a constant pressure. And the change in volume is just going to be the final minus the initial, which is zero. So we get negative uh, final pressure times final volume. So we now have our two works. Now what we can do is make use of the fact this is an adiabatic system, which means there is no heat coming or going. That means the change in internal energy is simply going to be, again, the initial internal energy minus the final definition of change in internal energy. And again, according to our definition of internal changes in internal energy, this will just be the sum of the work and the heat. But it's adiabatic, so that heat doesn't exist. So that heat is zero. And the work will be the sum of the compression plus the expansion. So we're just going to add these two terms together. So now what we've shown is the change in internal energy is going to be the difference in between the initial pressure and volume and the final pressure and volume. And again, this is fairly useful that we can use this for any sort of compression or expansion, but looking at this extreme case will be very handy. Now what we can do is rearrange this equation to show that this change is isenthalpic. Now what we can do is relate these initial internal energy and initial volume to the final internal energy and the final volume. Now when we do so, moving all the final terms to one side and all the initial terms to the other side, this is actually fairly useful because notice the internal energy plus PV equals internal energy plus PV. Now this should hopefully be ringing some bells because that's the definition of enthalpy. What we showed is that the final enthalpy is equivalent to the initial enthalpy, meaning the enthalpy didn't change. So we showed that if we have this compression and expansion from a low pressure to a final to a higher from a high pressure to a lower pressure, this will indeed be isenthalpic as long as the whole container is adiabatic. And again, this is a really handy proof. Now, in practice, I'm going to actually need to find a way to let this slow expansion of a gas from high pressure to low pressure occur in a little bit more of an elegant scenario. So what we do is we pump in a gas at a high pressure into a container that has a porous barrier. So this is often going to be something like a thick film or fiber where the gas has to slowly diffuse across the barrier, which will essentially slow its travel and make sure that we have a lower pressure on the outside. So we go from a high pressure to a low pressure. Then we can measure the pressures at each end. And then you can go ahead and put a thermocouple, which can just measure the temperature difference on the inside of the barrier versus the outside. So this will let us measure the change in temperature and the change in pressure, and we prove that the system will be isenthalpic. So that will give us the Joule-Thomson coefficient. So again, we make sure that we have a low pressure gas, which should have a different temperature. But the real question is, what should this temperature look like? And it turns out whether the temperature increases or decreases is entirely based on the Joule-Thomson coefficient. Because if the Joule-Thomson coefficient is going to be positive, well, if I have a positive Joule-Thomson coefficient, that means that as I decrease the pressure, I should also decrease the temperature. So I should see a temperature drop. This means I will cool the system. Congratulations. This was the for one of the first refrigerators ever invented. And this is still occasionally used, where you can use a gas that will have a positive Joule-Thomson coefficient. So as you let it diffuse, you will see this decrease in temperature. Now, the trick here is that this is also going to be due to having attractive intermolecular forces. Because if the gas has attractive intermolecular forces, it means it wants to stick together. It wants to have this high pressure. So as it goes across, we're breaking these intermolecular forces, which requires energy. And since the system is adiabatic, the energy has to come from the thermal energy of the gas itself, meaning we're going to decrease the temperature of the gas. So one of the first classic gases used in refrigerators, which with the removal of Freon we're starting to return to, is ammonia. Ammonia has great intermolecular forces, and so it has a pretty good Joule-Thomson. So there we go. You have your first refrigerator, often known as a Lindy refrigerator. Now, in contrast, if I have a negative Joule-Thomson coefficient, this means as I decrease the temperature, I should see decrease the pressure, I should see an increase in temperature. That means that as the gas diffuses, it gets hotter. It means that somehow it found some way to get more energy. Now, this is going to happen if the gas has repulsive intermolecular forces. So you're going from high concentration to low concentration. So if the gas really wants to get across, it can go ahead and use the energy from those repulsive forces. And with that energy being relieved, we move that into thermal energy, increasing the temperature of the system. And again, if you have a Joule-Thomson coefficient of 0, it means that the temperature on either side of this barrier should be identical, and this will happen for an ideal gas. So again, ideal gas will have a no temperature difference. If you have attractive intermolecular forces, this means you'll see a temperature drop. If you have repulsive intermolecular forces, you'll see a temperature increase. But just like we saw in chapter 1, it turns out that this will be very tied to the temperature and pressure of a system. So depending on the gas that you're interacting with and its compressibility coefficient, you will see different behavior. So again, in the region where your compressibility coefficient is going to be less than 1, you'll tend to see a positive Joule-Thomson coefficient. So if you'll notice, if I've got something like nitrogen with kind of intermediate forces, in a lot of realistic cases, so at pressures less than 100 bar, this is going to happen for temperatures somewhere in between like 150 Kelvin, so pretty much the point at which you're gas, all the way up to about 520. You get too hot, again, those repulsive forces start to dominate. You get too cold, and well, at this point, now you've got some particular issues because it wants to be a liquid. And you'll note that that exact temperature and pressure regime is going to depend on the gas. So if you have something with very low intermolecular forces like hydrogen or helium, this means that you'll have a very small region. Now, for a given pressure, we often are going to relate something called the lower inversion temperature and the upper inversion temperature. These are simply going to be the temperature bounds in which you're going to have a positive Joule-Thomson. So below the lower inversion temperature, you will be repulsive. Above the upper inversion temperature, you will also be repulsive. So again, this is a fairly useful thing. So again, for helium, the upper inversion temperature is about 40 degrees Kelvin because, again, helium has very poor intermolecular forces. For hydrogen, it's going to, at room pressure, it's going to be about 202. For nitrogen, it's all the way up to 621. By the time you're talking to something with even moderate intermolecular forces like methane at room pressure, it's all the way up to about 968 Kelvin. So again, meaning there is often a fair bit of choices for a good refrigerant, but a lot of the classic choices are going to either be chlorinated solvents, which are going to have very good dispersive interactions, or something with good hydrogen bonding, like ammonia. So next time, we're going to go ahead and look a little bit more at these adiabatic conditions we talked about with the Joule Thomson. So we're going to be spending a little bit more time on adiabatic expansions and compressions. Until then, take care.